Do you have a baghouse or dust collection system that doesn't seem to have the capacity that it once did after a modification to the ducting? Or maybe a system that was designed and had everything you wanted on paper, but once installed, just isn't performing, just doesn't have the flow that you need at the ventilation points. Well, maybe instead of staring at the baghouse or the dust collector wondering why that doesn't seem to pull as much air as it should, a better place to look would be the ducting and specifically the elbows, because the elbows that you choose will impact the system and ultimately your bottom line. My name is Matt Devitt with BWF Envirotec, and in this presentation, I want to talk about how elbow choices impact your bottom line. If you enjoyed this video, please like, comment, and subscribe. The feedback in the comments as well as the likes and new subscribers really help with the channel, as well as give me an idea of the topics you want to see covered, discussed, and put into more detail. So again, please like, leave a comment, subscribe, share with your friends. It all means a lot to me. So thank you. So let's get started. Ducting elbow choice is impacting your bottom line. But why and how? Well, elbows have a considerable impact to a ducting system's total static pressure. Therefore, when choosing an inefficient elbow, this will increase the system's total static pressure. Okay, but why do I care? Why does this matter? Well, if the fan was not designed to use the inefficient elbow and doesn't have the static pressure to overcome the increases to the total system static pressure due to the inefficient elbow used, the gas flow through the system will be reduced. With that being said, let's take a look at an elbow that nobody should ever use unless they absolutely have to, the mitered elbow. So, what is a mitered elbow? Basically, you take a pipe, cut it on a 45-degree angle, rotate one end 180 degrees, and weld. From the picture you see below, it doesn't take much to actually make an elbow or a corner in this system. These should never be used, and when found should always be removed. The only time that they should be installed is when the space is severely limited, and if they are, guide vanes should be installed into the mitered elbow to help reduce some of the loss. But with that being said, it will still have a considerably higher loss than a standard elbow with a gore. Okay, you say, kind of makes sense, but what is an elbow gore? Good question. So an elbow gore is just the number of segments in the elbow that change the direction of the elbow. Common gore counts for an elbow are 3, 4, and 5 gore segments. The more gores, the lower static pressure at the same elbow radius. If you want to go to a system that's lower resistance than a high number of gore segments, then going with a smoothbore elbow, also known as a stamped or die-formed elbow, will give you the lowest static pressure, again comparing across the same radius. Now that we've touched on different types of elbows, the mitered elbow and why it shouldn't be used, as well as gore segment elbows and even the stamped form smooth bore elbow, let's take a look at a ducting system example where we install different elbows and see how that impacts the overall system resistance. With that being said, we want to have a baseline. So the systems that we're looking at are all going to be at STP conditions, or standard temperature and pressure, and it's going to be dry air. The flow through the system will be 750 ACFM. All of the ducting will be 6-inch diameter duct, giving us a transport velocity in the ducting of 3,820 feet per minute. There's a total of 50 feet of straight duct. There will be 3 90-degree elbows. In this example, we're going to start with using the mitered elbow, and the hood has been optimized to have a low static pressure. With the mitered elbow being used in this example, this is actually going to give us the highest resistance, which is why we're going to start and take a look at it. With that being said, the hood loss within this system is 1.14 inches of water column. The duct loss is 1.97 inches of water column, where just the elbow loss by itself between the 3 elbows is 3.27 inches of water column. So when we look at the total system loss in this system, 51% of the total loss is coming from the 3 elbows. And this is substantial, specifically if the system was designed for the next example where we actually use a 5 gore elbow. In this system, same fan, same flow rates we want to have going through it, but we're going to use a 2 radius 5 gore elbow. This will give us a considerably lower resistance. In this system, by having the same flow going through it, what you'll end up noticing is that the overall static pressure is going to be considerably less. Now, the hood loss will be exactly the same hood in both systems. So we get 1.14 inches of water column. Duct loss, again, exactly the same. There's still 50 feet of straight duct within this system, giving us a system loss of 1.97 inches of water column. Here's the interesting part. The total elbow loss between these 3 elbows right here is 0.52 inches. The previous system was over 3. So we've created a very, very large reduction if the system had the mitered elbows in it, and it was designed for a mitered elbow. Conversely, if the system was designed for what we see right now with the 5 gore 2 radius elbow, but for whatever reason in the field it was installed with mitered elbows, that system would end up only allowing for a flow of about 35% of that 750 ACFM at the hood itself. Therefore, capacity on the system is considerably lower because of the elbow choice itself. Also, another way that you can approach this problem, which is to look at rearranging the actual system itself. So what we did here is maintained the same 5 gore 2 radius elbow, but removed 2 of them and effectively went straight up from the hood for 40 feet, made a 90-degree turn, and then 10 feet of duct directly into the baghouse hopper. Let's see what this does to the overall static pressure by removing 2 of those elbows. As you probably guessed, by removing 2 of the elbows and still maintaining the same amount of total duct run in the system, the overall static pressure did decrease, and that decrease was seen in the elbow loss itself, effectively becoming 1/3 of what it was in the 3 elbow system. Again, considerable. So if we think about these 3 systems, if the system itself was designed for 3 elbows at 5 gores, and in the field 3 mitered elbows were installed, then the system would never ever create the same flow that's required for proper collection at the hood. If we look at the other extreme, or the right side of this table, where we have 1 elbow at 5 gores, the total static pressure of the system will actually be lower than design. Therefore, the fan will actually pull more air or gas through this system, at which point dampering would be required, or a variable frequency drive or variable speed drive on the fan, in order to capture some of the power savings by having a more efficient system because of removing the elbow and, again, lowering the overall static pressure of the system. So what have we learned? Well, I hope if I've done my job right, there's 3 points that you'll walk away with. The first one being, mitered elbows should always be removed and never installed. Yes, I gave the caveat that if the only way you can make the 90-degree corner is with a mitered elbow because of space constraints, then you do what you have to do. But if properly planned, a mitered elbow should never ever be used. The second point is the way a system is designed is the way it should be installed. As we showed in these systems, if it was designed for 3 elbows with 5 gore segments and mitered elbows were installed, the system will never ever be able to hit the design flow rate it is required because of the increased static resistance into that system. And lastly, always use the most efficient elbow that fits the installation space required. What this means is if you have the option between a 5 gore elbow but a 1 radius or 2 radius elbow, if the 2 radius elbow fits, use that one. It will give you a lower static pressure than the 1 radius elbow. I hope you found this presentation informative. If you have, please like, subscribe, take a look at some of the other videos that I have on this topic. Your feedback is important, and I'd really appreciate if you shared this with other people that would find it useful. Thanks.